So we're going to take a look at two source interference patterns, and when I say two source, I mean either there's actual 2 point sources like two little lamps or whatever, or there's two source in the sense that there's one source out here somewhere and then there's two gaps in something, two slits in something. So they act like point sources because as the wavefront comes through it starts to diffract. Either way, you get these nice little interference patterns, or they would be nice if my drawing was better. So what we're going to do is, one, assume that my drawing is great and not as terrible as it looks here. And second, we're going to look at what happens with the constructive and destructive superposition of the waves. So you came across this last year when you see two wave fronts meeting each other, two wave fronts meeting each other, two wave fronts, just imagine that's all in the one line. You're going to get constructive interference all the way along there. And look, here's two troughs meeting and two troughs meeting. And what you end up with is, and just assume that these two actually cross there like they should, what you end up with is a place where you get bright light or loud sound, depending on what type of wave you're talking about. Or presumably, if it was water waves, you'd get high amplitude, big wave. So you then get a place where there's destructive interference, where a peak is meeting a trough, and 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 you end up with a place, an area where it's dark or quiet or flat. Okay, and the same thing, if you look out here, you get another place where there's constructive interference. Okay, where again it's going to be bright or loud. Now last year you got introduced to the idea of path difference, and this year we're still going to use that same concept, but we're going to apply it in a slightly different mathematical way. So again, we're going to say we have 2 point sources, and we're going to say, well, the distance between these 2 point sources is D, and we have a screen, and this distance here between the point sources and the screen is L, okay, and we will get, along this midline, we will get a bright fringe, but we'll also get a bright fringe, say, here, okay, and I'm going to draw this triangle in a different colour. This is a bright fringe that's happening not on the midline. So what we can do is, and say, well, please excuse again my terrible drawing, there's a path difference between these two wavefronts. This is how far the wave has to travel to get from this source to there and that source to there. There's going to be a path difference between it, and last year you would have learned, hopefully, that that path difference is going to be some whole number multiple of the wavelength. Because you can see, I hope, that if this distance, this extra distance that it has to travel is one whole wavelength, by the time it reaches there, they'll be completely in phase. There'll be constructive superposition all the way along this, this point, this line. Now the thing that, the mathematical jiggery-pokery that we do in order to get some nice maths out of this, in order to solve problems, and if you object to mathematical jiggery-pokery, now is not a good time to express that feeling. So we're going to do some mathematical jiggery-pokery, and the net result of that mathematical jiggery-pokery, which I'll explain to you if you want, but like not now, the net result of that mathematical jiggery-pokery is that we can come up with a formula that for any antinodal point, for any bright place or loud place, for any fringe you might call it, we can use this formula that n lambda, the number of wavelengths difference, is equal to d, the distance between the points, x, this distance here from the midline to the fringe, over L. Now this only works, and this is why I say mathematical jiggery-pokery, this only works if x is tiny compared to L. And it relies on the fact that the tan of an angle and a sine of an angle are pretty much similar so long as the angle's small. So if you are affronted by this maybe now's the time to reconsider being a physicist or an engineer, because basically we love things that simplify even if they're not quite perfect. So if x is smaller than L, a lot smaller than L, this formula will hold true for any nodal point, any antinodal point on the line, sorry. If we're interested in a nodal point, I hope that you can look at it and go, oh, well, in that case, n's just going to be like a half, okay? And what we actually do is we say that's n minus a half lambda also equals dx over L. And that minus a half is to do with the fact that this is the 0 fringe, that's the 1 fringe, say. This is the half fringe, so it's 1 minus a half. Okay, not plus a half, minus a half. And that's because this is 0 and that's 1. Okay, we can use this to solve problems. Yay us. But first we're going to go on to diffraction gratings.